Yeah, so it's a historic module because this is only the second iteration of it. So this was actually a module created and implemented for the first time last year to rave reviews. And we've gotten some of the feedback from that and kind of implemented it this year to the extent that we can. And so this is really only the second iteration of it. It is also, to my knowledge, the first laboratory course of this subject matter ever taught at MIT, which is perhaps surprising given the importance of the subject matter we'll discuss. But anyways, so this course is really about kind of giving you hands-on experience with the experimental chemistry that relates to renewable energy, right? And a lot of chemistry touches on topics of renewable energy, and what we'll focus on in this particular one is renewable energy storage. Ways essentially to interconvert electrical and chemical energy. That's really the goal of kind of all of the experiments that you'll do in one flavor or another. And what that really centers on is understanding this field of, or subfield of electrochemistry. Right? This is where electrons are used to drive chemical work and make and break chemical bonds. And if you can do that efficiently and selectively, you can store intermittent renewable electricity in energy-dense chemical bonds, and that's really where chemistry plays a central role in problems related to a renewable energy future. And some of this already exists. Some of you may have taken trips in a zero-emissions fuel cell bus. In this bus, you don't burn gasoline, you instead burn hydrogen. And importantly, you don't even kind of burn it at all, right? Because burning implies that you have a spark and you light it and it kind of explodes, which is what happens inside an internal combustion engine. But what you actually do here is you input a fuel, oftentimes hydrogen, but not always hydrogen, and you do what's called cold combustion. So you do react the fuel with O2, but you don't do it at very, very high temperatures. You do it at very, very low temperatures, modest temperatures, like 80 degrees or so. We were both in the same. So the hydrogen reacts at an electrode, and what that does is produce protons that move across an electrolyte membrane. The electrons get sucked out to an external circuit, and on the other side, those electrons reduce O2 to water. So in net, the reaction is hydrogen plus oxygen, but it doesn't go boom. It rather is in a controlled fashion at two electrodes separated from each other spatially, and what you're extracting from that is electrical work energy. This is enormously powerful, right? Because you probably all learned that if you do combustion, the energy you can extract from any reaction is going to be limited by Carnot efficiency, right? And what that relates to is that if you have a heat engine and you're trying to extract work from that, it's the relative temperature differences between the hot and the cold that set sort of the efficiency of ever converting anything that generates heat into something that generates electricity. And so the Carnot efficiency of a system that does high temperature combustion is really limited by the temperature separation, and oftentimes that works out to values on the order of sort of 30–40%. Because this is cold combustion, you are not limited by Carnot efficiency. You can, in principle, extract all of the work energy that's in the chemical bonds of H2 and O2. In practice, doing this places enormous strains on developing efficient catalysts for these reactions. And we'll talk about that in great length. That's actually what a lot of the course will be on, is understanding how to catalyze reactions effectively using electrons. But nonetheless, this is a device that is having greater prominence in the transportation sector. This is a reaction where you use electrons to drive chemical work and chemical bonds. Of course, batteries also do this, right? So all of the sort of portable device revolution was facilitated by a pretty impressive invention in how you storage charge in lithium ions. Without lithium-ion batteries that all of us are carrying around in many iterations with us, we would just not have a modern digital economy, right? And so electrochemical advances are really societal advances, at least in recent years. And I think that'll only continue because electrons are really the reagent of the future. Of course, there's many emerging reactions you can do, including using electrolysis technologies, kind of the reverse of a fuel cell, to, for example, reduce CO2 to products, and in principle close the anthropogenic carbon cycle, something that would also be very valuable to be able to do. So this is a very old field on the one hand, but it's also a very sort of growing and burgeoning field because there are a lot of new techniques, new synthetic methods, new spectroscopic tools that have been applied to understand the types of reactions that we're going to be studying. But this really, you could say the father of modern electrochemistry was Michael Faraday. He actually coined many of the terms that you'll see in your lab write-ups and in your notebooks and that you'll use. So remarkably, I mean, it's kind of amazing how much Michael Faraday did, but he helped coin terms like cathode, anode, electrode, and ion. Isn't that amazing? He coined the term ion. This just was amazing to me, right? And in where it came from, right? So cathode refers to descent, and anode refers to ascent, which refers a little bit to his conception of where the electrical work energy was going, right? And so, of course, we now use this in more general terms to denote where electrical charge is flowing, but he really came up with these laws. And in fact, that's why Faraday's constant is named after him. It's actually the number of electrons, number of coulombs in a mole. He also discovered the first electromagnetic induction motors, which are really what we use right now, induction drive motors for pretty much everything. He discovered benzene. It's amazing. This guy's just absolutely amazing. He was the first to make carbon-chlorine bonds by liquefying chlorine for the first time. And he did some of the earliest work on gold colloids. So, of course, now the people who did the earliest work on gold colloids were monks that were making stained glass windows. But they didn't exactly know they were working with gold colloids. So Michael Faraday actually did some of the first work on kind of observing the optical spectra of gold colloids. Really a very, very prolific individual, and he discovered diamagnetism. This guy's amazing, absolutely amazing. He's definitely one of my scientific heroes. Again, at a time basically when people were not professional scientists, they were basically hobbyists. Right? So these people were like people who were either independently wealthy or had resources from other things, and they just basically like do science as a hobby. Right? And Michael Faraday is actually very well known at the Royal Society for giving these elaborate demonstrations where he cart out like capacitors and voltaic piles and other things like that, and he'd show electrical charge going from various places and how to move a magnet. And they basically were kind of like magicians a little bit, except they did science too. It was really an amazing time. Okay, so what those kind of terms refer to is really related to something that, again, Michael Faraday didn't have a full appreciation of at the time, but we now have a much more evolved appreciation of, which is that whenever you do electrochemical reactions, you're going to involve an interface. An interface would usually be the interface between a solid and a liquid, or a solid and an electrolyte, more precisely, right? And so, to a large extent, the study of electrochemistry, or the study of how you use electricity to do chemical work, is the study of interfacial chemistry, the chemistry that occurs at the boundary between a solid and a liquid. And so there are many things that we're going to kind of go through a litany of that will allow you to get an intuitive sense of how to think about how interfaces behave, right? And so the first thing to appreciate, right, is that indeed electrochemical reactions are interfacial. And so how you can think about this is that you have some solid electrode, usually this is a conductive metal, and that metal you can apply a charge to, right? And if you apply a charge to it, what tends to happen is that equal and opposing charges reside outside of that metal in the solution. And this creates a very, very strong local electric field that can be used to drive reaction chemistries against their native thermodynamic free energy profiles. And then you have a bulk of a solution that can then deliver species to that interface. You have a region over which diffusion is the dominant force by which things move. And then this double layer really designates where the sort of action happens. So this is the key takeaway. The reactions that really matter are the ones that occur right at the interface. And we still have a lot to learn about how these interfacial reactions occur, but I'll give you kind of a little bit of our understanding of how that works, and that little bit has still been enormously powerful. So because electrochemical reactions inherently occur in an interface, they are sort of always characterized by a disequilibrium in homogeneity, both across space, meaning how far away you are from the electrode, and oftentimes even across time, because you can vary the charge state or the potential of this electrode in time. So the aspects of gradients in things moving and changing their chemical potential are everywhere in electrochemical science. Okay, so how can we understand this a little bit further, right? So basically, all of the kind of mechanisms that you learn about in, say, organometallic chemistry or in organic chemistry, we understand that in general, right, mechanisms relate to kind of understanding the individual sequence of steps that occur over a given process, right? And in an electrochemical system, you're also understanding mechanism, but these types of mechanisms are just a slightly different kind of mechanism. And the reason they're a different kind of mechanism is that they don't only involve activation-controlled processes. They also involve diffusion and convection because you're at an interface. I hope that makes sense. So there are elements of this mechanism that involve mass transfer. You need to move reactants or products from the bulk of a medium to a region near an electrode to be able to do a reaction. You also have chemical steps, right? Things that are divorced to a large extent from the reaction occurring at the interface, but are nonetheless important to the mechanism. This could be, say, a molecule isomerizing to a different shape, or it could be a ligand dissociating from a molecule, right? There are many reactions that are not explicitly influenced by the electrical potential, but are nonetheless essential to doing the overall reaction. And so there are many chemical steps that can be in play. And then you can have reactions that also occur at the electrode, right? For example, molecules can adsorb or desorb from the electrode. Adsorb or desorb are just fancy words to say that they bind to the surface and then debind. Surface chemists tend to use the word adsorption rather than just chemical binding, right? That's how we would think about it in many other flavors of chemistry. So things can bind to the surface, they can debind from the surface. Remember that all of these things, every individual step is going to be governed both by a kinetic parameter, the rate of the forward and back reaction, as well as some thermal chemistry, right? The ratio of those rates, essentially, what is the equilibrium position of, say, this adsorption-desorption equilibrium or some other process that might occur. Now, all the while it is adsorbed, or even before it is adsorbed, it can engage in some electron transfer reaction, right? So it can take an electron from the electrode, give up an electron to the electrode, and of course, those processes of taking and giving up the electron from the electrode are the ones that are most principally dependent on the actual potential of the electrode. We'll define very precisely what potential means in a moment, but you have all of these sort of steps occurring while you also have the ability to transfer electrons at the surface between the electrode and something in solution or something that's bound to the surface. Okay. The other thing that's really important to appreciate is that one of the grand things about electrochemistry is that you are very, very easily able to measure the flow of that current, right? So because it's an electrical measurement, you can literally count the number of electrons flowing through your external circuit. That's just a measure of current. But what's so powerful about electrochemical systems is that a measurement of current is a measurement of rate, right? Because if I pass current and I know what reaction the current is going towards, by counting the amount of current per unit time, by simply appreciating that an equivalent of charge had to go into an equivalent of a molecule or an equivalent of a reactant by some stoichiometry, I then essentially know the rate of the reaction occurring. That's incredibly powerful, right? And since I can measure currents all the way from sort of picoamp and nanoamp levels to many amp levels, I have many, many, many orders of magnitude over which I can sample the rate of a reaction. That's enormously powerful, right? If I wanted to measure a reaction in solution that was occurring at a rate of, say, that much of a change, 6 orders or 7 orders of magnitude change in rate, I'd be very difficult to do that because there are not many other tools that are that incredibly sensitive. Electrochemistry is very, very sensitive, but one thing that electrochemistry is not so often useful at, right? Just because I know that electrons are flowing and I can count the number of them that are flowing does not a priori tell me what they're flowing to, right? And that's both kind of the amazing thing about electrochemistry is you have enormous sensitivity in knowing that electrons are flowing. You have comparatively little sensitivity in knowing what they're flowing to. That's kind of the double-edged sword here, right? So I may know that I'm passing a nanoamp of current. I may not know what that nanoamp of current is going to, what reaction it's doing, right? And so on the one hand, I know rate very, very precisely. I don't necessarily know what the rate's going to very precisely. We'll talk about that. There are ways to surmount that through a combination of other methods. Okay. So that's the main thing I want to take away from the slide, actually, right, is that and we'll walk through the nitty-gritty details of how actually a potentiostat, the machine you'll be using in lab, actually works. But to a first approximation, how it works is that you have a power supply, and the power supply will apply a large voltage. That large voltage will be applied between two electrodes, right, because in any electrical sort of circuit, I need to have a complete circuit. And that complete circuit is where I have a power supply driving electrons into one electrode. This is often referred to as the working electrode, and then taking electrons out, or vice versa, from what's known as a counter or auxiliary work electrode. And what's completing the circuit is the fact that when electrons flow through here, ions are flowing through the solution. So it's not an open circuit, right? Because what this looks like is I've got a power supply and two leads. But of course, if I have a power supply and two leads just in air, right, I'm not going to get any current to flow. And the reason is there's too much resistance between the air. But when I put it into a solution that has electrolyte, I can move ions now equal and opposite to the flow of the electrons. And so the circuit is essentially being completed by the ionic flow in solution. And in fact, the rate of that ionic flow, or the resistance to ionic flow, determines how much power I need to apply here. But oftentimes I don't care so much about how the ions are flowing here. What I rather care about is making sure that the applied potential of this electrode, remember voltage is a potential separation, but the potential of this electrode is something I can measure relative to a reference electrode. We'll get to that in a moment. So what does it really mean to apply a potential? So an electrochemical potential is really, really such a basic concept. But so many people don't understand this, right? So when we say electrochemical potential, it's really important to appreciate that electrochemical potential has an electro term and a chemical term, right? So an electrochemical potential is really relating to equilibria that are both related to the chemistry of what's going on and the electrical potential that's impacting that chemistry. So, and that's kind of reflected in all of these equilibria, right? So when I write an electrochemical equilibria, it by necessity has chemical species and it has electrons. And because it has chemical species and electrons, the work energy or the relative energy of those electrons is going to influence the equilibrium position of that reaction. So for any one of these reactions, you can see that there's no requirement on the relative stoichiometry, right? You can have things that have a single atom but many, many electrons and protons. You can have something that has relatively few electrons and protons but many heavy actors. There are tables that are literally hundreds and hundreds of electrochemical half reactions. By the way, the reason they're half reactions, right, is that they have a net electron in here. If I do some other reaction, let's say as an oxidation, I can balance the electron flow. And that always happens in an electrochemical cell, but these are just a set of tables of electrochemical half reactions. The important point to be appreciated, right, is that when I'm able to alter the charge state of my electrode, I can alter the potential or the work energy in these electrons. As a result, I can alter the position or the relative driving force of any one of these reactions. Whether that change in driving force leads to a change in rate is far more complicated, and we'll talk about that at great length over the next little while and also the next time we meet. But for right now, all I want you to appreciate is that by changing the potential of my electrode, I'm changing the essential work energy that these electrons can provide. And as a result of that, I'm changing the driving force for any one of these reactions. In other words, I can change the reaction quotient from being, say, 0.001 to being like 1,000. Right? I can change it from strongly favoring products to strongly favoring reactants simply by changing the energy of one of the participants in this equilibrium. Okay, so that's really key, right? And in fact, I can go even backwards, right? So I can take any one of these reactions, and by determining what potential I need to apply to make sure this is in 50-50 equilibrium, I can determine the potential. So most people don't appreciate this. A lot of our understanding of the thermal chemistry of things in solution actually came from electrochemical measurements and electrochemical equilibria that were constructed off of those measurements. So the reason we know, for example, the difference in energy between tungsten oxide and tungsten is because you can measure that electrochemical potential difference. Extremely powerful. Most of our understanding of thermodynamics actually comes from electrochemistry, but it came so long ago that most people don't really appreciate that was the case. Okay. So again, this is a restatement of this, but a clear correlation of understanding how the reaction quotient of a reaction, the ratio of products to reactants, can be related to the applied potential for any electrochemical half reaction using what's known as the Nernst equation. And Nernst equation simply relates the potential that the system is subjected to relative to some equilibrium potential value and a factor term here that's 59 millivolts over the number of electrons transferred and the base 10 log of the ratio of the oxidized and reduced forms. This reaction quotient is like any other reaction quotient, right? And so that means that if, for example, there's a stoichiometry to a particular unit here, that will appear in the exponent. So just to do a very quick exercise, right? If you, for example, were to write, let's do something. So let's do for this nitrate reduction to nitrite, right? The quotient here, right, would be products over reactants. Well, okay, these are always written as reduction reactions. So if we want to use the reduction potential as the E naught, we would say, okay, the product of the reduction here is the nitrite. So this is written as ox over red because this is plus. If it were red over ox, that would of course be minus. But if you write reduction potentials and you do it with in this case it's going to be ox over red. But in any case, the point I want to make is that whatever side of the equilibrium it is, right? This would have a concentration term in nitrate. It would also have a concentration term in proton, but very importantly, that would be raised to the exponent 2, right? And that's because there's a stoichiometric coefficient of 2 here. And as a result, then on the product side, you have nitrite. Water has unit activity, so even though it appears in the denominator here, it won't, of course, vary with the Q, right? If you're in an aqueous medium. If you're not in an aqueous medium, it would have some finite activity. Does this make sense? This is like writing a reaction quotient for any other reaction. The only thing that's pulled out of here is a dependence on potential because there are electrons in this. And the reason the number of electrons comes out here is because, again, they're related in a stoichiometric fashion to the overall reaction. Okay, so you can write out electrochemical equilibria using the Nernst equation for an awful lot of different things. And you can learn then, for example, how the potential will vary with, say, for example, the change in the pH, right? If I change the pH in a certain fashion, that'll change the potential in some way. And so let me ask a question here. Let's compare. Let's see which one we'll compare. Okay, let's compare the nitrate reduction and nitrite versus the nitrate reduction to ammonium. Which of these two reactions will be more dependent on pH?
The second one.
Okay, why do you say that?
Because there's more pluses and equations, so it raises the
Yeah, but there's one other piece also, right? Because if you look at this, right, if I look at how the potential is changing, this exponent term is going to be multiplied by a value over z, which is the number of electrons. So if you notice here, there are more protons certainly here, but there are also more electrons. But importantly, if the number of electrons and protons was equivalent, because that factor here, the exponent here, would equally cancel by the number of electrons here, the shift in potential would simply equal that 60 millivolts. But you're right, because in this expression, there's actually more protons than there is electrons. And so because there's an off stoichiometry of those, the dependence on pH is more pronounced than what we call Nernstian scaling. So this term I'm going to throw out here, right? So many reactions depend on pH, but some are referred to as having a Nernstian dependence on pH. What that means very specifically is that the way in which it scales is just 60 millivolts per pH. And that usually occurs when a particular reaction has an equal stoichiometry of electrons and protons. When there's an unequal stoichiometry of electrons and protons, the scaling with respect to pH is, and these are terms that are not used generally, but I'll use them, sub-Nernstian or hyper-Nernstian, which is to say that it moves by more than the 60 millivolts per pH or by less than the 60 millivolts per pH that you would expect for equal stoichiometries of electrons and protons. Okay, well, this will come up in more detail in an actual lab module, but this is just kind of give you a primer on that. Okay. The other important thing to appreciate in electrochemistry is that you cannot control the current and the potential independent of each other. Right? The system determines how current and potential are related to each other, and they're related to each other by the kinetics of the underlying reaction, right? So that's really, really important to appreciate, right? So it's kind of like in homogeneous solution, you can set the temperature for one given reaction. Say I did reaction of A going to B and it had a certain rate constant, right? I can vary the rate by changing the temperature, or I could vary I could vary the temperature and measure the rate, or I could set the rate, and if I had something that would toggle my temperature, then I could make the thing that toggled the temperature find the appropriate temperature for the rate I desired. And the same thing can actually occur in electrochemistry. It's actually easier in electrochemistry because you can have your machine, your potentiostat, either set the potentiostat, or set the current, which is known as galvanostat, right? So all potentiostats, essentially all potentiostats are also galvanostats. And in fact, the earliest electrochemical equipment was not a potentiostat, it was a galvanostat, right? Because what you need to do to have a potentiostat is have some more complex electronics than what you need for a galvanostat. In fact, all you need for a galvanostat is a few large batteries and a large resistor. That's really all you need. And you can make a galvanostat like literally with like a few parts, like under $5, you can make a galvanostat. But the point to appreciate is just like in solution, you can set a temperature and measure a rate, or in principle, but very difficultly, set a rate and then measure a temperature. In electrochemical systems, these are equally easy to do. You can set the potential and measure the rate, which is the current, or you could set the current, the rate, and accept the potential. So that means if I had a given reaction and I wanted to make sure it had to go at 100 times per second, I could set the current necessary to achieve that, which would simply be that 100 times per second times some constants for Faraday's constant number of electrons. And if I did that, I know what current I had to pass to equal 100 turnovers per second. And then if I set that value, I can then measure the potential necessary to sustain that value. It's extremely powerful, because you can do them both in reverse in a way you can't easily do in homogeneous solution. Okay. And that's the thing, that you can't control both at the same time, you can control one and measure the other. Okay. So how does this actually work in practice? So everything I'm kind of giving you now is sort of the kind of baseline rules of how to think about electrochemical systems. What we're going to do for the next little while is really kind of talk about some of the practical aspects of how you do an electrochemical measurement, what's really happening when you're applying, when you have leads touching electrodes and they're varying things in your cell, right? And I think it's really, really important to have a really good physical picture, because many, many people who do electrochemistry push buttons and don't really know what's happening. And that can, and the thing about it is, the cool thing about electrochemical systems is that you get data very, very quickly. And so if you can make game time decisions as to what your data is telling you in terms of the next experiment, you can be very, very effective in collecting electrochemical data. But that really requires a good physical understanding of what's happening. So just to kind of recast, right? If I have two electrodes, most of the measurements you'll be doing are 3 electrode measurements. And what that means is that they consist of 3 different things that are in contact with the solution. First is a working electrode, the second is a reference electrode, and then a counter electrode. If I have no potential applied or no voltage separation applied between the working and the counter electrode, that does not necessarily mean that they are not charged. Right? That's the first thing we got to take away, right? All it means is that the potential of the working electrode and the potential of the counter electrode are the same. That's why there's no current actually flowing between the two of them, right? Or there's no potential separation. under any set of conditions, right, my external power supply, if I wanted to, will apply a potential separation between the two. And that will drive an additional charge separation to, for example, add more negative charge here and correspondingly add more positive charge to the counterelectron. And what I think is valuable to really do is to think about, okay, when I have that third electrode, you can think of this reference electrode as essentially an electrode that will sense the potential in the solution. And the way it will sense the potential in the solution is that it will have a reference reaction inside of it of a known potential. One of the electrodes you'll probably use in the lab is known as a silver-silver chloride reaction, and it is setting the potential relative to the equilibrium between silver chloride and silver plus chloride, right? And then because you're reducing silver 1 to silver 0, that's an electrochemical half reaction of a known potential, and so you can reference all your other potentials to that value. So how does the actual system look like, right? Because these two electrodes are charged under either the condition of having no applied potential or having some applied potential, the way the field profile really looks at the interface is something like this, right? Because I've accumulated an awful lot of charge at my working electrode, what that's essentially created is a field gradient at that surface. In other words, I have negative charges on my electrode and a lot of positive charges near it, and since the positive charges are screening the negative charge, the effective electrostatic potential at my surface is higher than that of what it, or more negative than what it is in the bulk, and these positive charges are screening that, and so by the time I move even a few tens of nanometers away from the electrode, the electrostatic potential at the surface has fallen essentially to a value that's 0. It's not to say the electrochemical potential has fallen that way, but the electrostatic potential has fallen. And because the counter electrode is also charged, there's an equal and opposite polarization of that electrode. Oftentimes you don't care what's happening at the counter electrode, and so you're simply measuring what the working electrode is doing relative to the reference electrode. But the field profile you can think of as behaving something like this. And this is under the condition before I even told my potentiostat to apply something. So what you'll see is that if I then add a potential, right, if I take my driving big power supply and have it apply more of a charge separation, I can make more electrons go into here and therefore make more positive charge go into here. And that will motivate a current to probably flow, right? And if a current is in fact flowing, right, the current that's flowing over here has some resistance to its flow. And that's what is known as a resistive loss, or an IR loss. It's an ohmic loss because it's associated with simply the current flowing through the solution. And you're able to minimize some of this resistive loss by having a reference electrode. In fact, that's one of the reasons you have a reference electrode, not only to pin the potential or to measure the potential relative to a known value, but also to essentially compensate for or remove a lot of the resistive loss that's occurring between the reference and the counter electrode. And so oftentimes you'll want to position your reference electrode reasonably close to your working electrode so as to minimize uncompensated losses in resistance. And the reason that's happening is because, remember, ions have to flow all the way from the working to the counter for every equivalent of charge that goes through the system. But I don't want to have to worry about all of that resistive loss in solution when I'm measuring my potential. This is a subtle concept. Does that kind of make sense? Okay. I know this is a lot to digest, guys, in a field you've probably never experienced before, and that's totally fine, but please interrupt me because I can really go at a pretty fast clip, and I don't want to. I just want to make sure everyone's getting everything. Okay. So when I've applied this potential, right, I might have lost some in solution, but I can often compensate for that by having my reference electrode close to my working electrode, or using even more fancy techniques, which we won't really go into right now. The point I want to make is that any amount of uncompensated resistance means that the measured potential I apply needs to be subtracted from some of this resistive loss. And as a result, the potential that I'm actually measuring is a little bit off from the real value. And it's off from the real value by this resistive loss relative to my reference electrode. Right? And so I think we do a little bit in the lab about how to minimize these resistive losses and why a reference electrode is valuable. Okay, so if I know something overall about how the cell is working, let's dive a little bit more deeply into what's really happening at my electrode when I apply a potential. Right? When I apply a potential, what's really happening is I'm moving electrons to that electrode, and that's causing a local reorganization of the counterbalancing charges. So let's just take a look at that again. Right, let's take a look at that again. Maybe a few more times. Okay. It took me a long time to make this. So, but the big takeaway, right, is that most of the charge that is screening this negative, I'm choosing this in this case to be negative charge on my electrode, right, is being screened by a lot of positive charges right next to that electrode, right? And of course, the electrode itself, right, is blocking the ions that would want to interpenetrate. Now, that's not true for all electrodes. There are certain electrodes that are not ion blocking. They're what are known as ion penetrable electrodes. And as a result, this picture breaks down in that case. But for most of the electrodes you'll deal with in the lab, at least over the regions that you're polarizing, they are essentially ion blocking. And because they're ion blocking, what you get is this very, very sharp electric field gradient. Now, all electric field gradient, right, arises from the fact that you have a separation of charges, and you have a separation of charges right at this interface, and because of that separation of charges, there's a very, very large potential separation. And that very, very large field there can drive reactions at that interface, essentially. But the important thing to realize is that this field is screened very, very quickly by the ions in solution. So there's a term called the Debye screening length, and that just essentially refers to how quickly, as a rough approximation, is the field screened. And for most of the electrolyte solutions you're going to be using in the lab, the field's going to be screened very, very rapidly, over the order of less than about a nanometer, really very, very sharply. And so what you want to think about when you're polarizing an electrode is that you're really changing the character of the local field right at the electrode surface. And that's causing a perturbation in the nature of the reactions. Okay, now if I polarize that electrode, even with nothing in solution that's electroactive, if I polarize that electrode a lot, like on the order of many volts, right, eventually I can drive reactions that we have no business doing, right? For example, I can rip apart the solvent itself, right? And this is why every solvent has a solvent window. It's the window over which I can apply a potential without just wrecking the solvent itself, right? And so different things based upon their chemical character have different solvent windows, right? And so, for example, acetonitrile has a solvent window that's pretty large, on the order of around, again, this is for very pure acetonitrile, on the order of probably around 5 volts or so. And something like chloroethane has a smaller, ethene has a smaller charge, dichloromethane has a smaller solvent window. And of course you can see that different solvents, so dimethyl ether, dimethyl formamide, DMSO, have different solvent windows not only in terms of their width, but also in terms of where they are. And this is essentially telling you how easy is it to oxidize or reduce this solvent molecule. So let's take a good example, right? So for example, something like acetic acid, right, is relatively hard to oxidize, right? Because it's an acid, it's a pretty strong acid, but it's very easy to reduce, right? It's because it has a proton here. And as a result, if I'm able to reduce those protons to H2, that's going to limit the negative solvent window. Whereas you look at something like THF, or you can have a very, very negative solvent window, something like HMPA, a very negative solvent window, and that's because there's nothing easy to reduce on this molecule. You can go even further. There are ionic liquid media that can expand the solvent window even more. I think probably the largest solvent window ever recorded was on the order of probably around 8 to 9 volts in certain ionic liquids that are very, very pure. The other thing that's really important here is that in all of these cases, if you have small amounts of impurities in your electrolyte, that can dramatically alter the solvent window, because of course then the impurities themselves can be reduced or oxidized rather than the bulk solvent. Or the impurities can facilitate the oxidation or reduction of the bulk solvent in one way or another. And of course, this is also dependent on the nature of the electrode, right? If I have an electrode that's very catalytically active, like platinum, its surface can catalyze reactions that, for example, just a carbon electrode would be unable to do. GC here refers to class C carbon. It's a variant of graphite. So you can see that the solid windows for, say, gold and platinum and glassy carbon are different. And of course, they're different because the surfaces have different catalytic activities. Okay, so this is another practical aspect. What solvent am I going to choose to do a reaction? So there's actually some work occurring in our group where we're trying to do high temperature electrochemistry in a molten salt. And it's very important to choose that molten salt right so that you have a large enough solvent window to do the reaction that you want to do, especially if it's a very hard reaction. Some of the reactions we're trying to do are very, very kinetically challenging. Okay, another practical aspect, and we'll stop after a few more slides, is this issue of what you're going to choose for your reference electrode. Right? So for your reference electrode, you can choose a lot of different possibilities, and these are really designated or binned by the type of reaction that's occurring in that reference electrode. So for example, a silver-silver chloride electrode, as the name might imply, involves the electrochemical reaction of silver metal going to silver chloride. Right? So the reaction quite literally is silver metal oxidized by one electron to make silver 1, which then interacts with chloride to make silver chloride. Right? And in this other case, it's mercury going to mercury 2 sulfate. For mercury oxide, it's going to mercury 2 oxide. The normal hydrogen electrode is the reversible reaction of H plus going to H2. And so all of these have independent electrochemical reactions. And the important thing about a reference electrode is that you want that electrochemical reaction to be so darn fast that even if I pass an equivalent of charge through the system, a small amount of charge, I won't move the potential very much. In other words, reference electrodes are what is known as ideally non-polarizable. They're unable to take on a potential because they do a reaction that sucks that potential away. It may be hard to appreciate, but let me just say that for a second, right? So if I have a really fast reaction, like silver going to silver chloride, if I try to push my potential a little bit to the positive or a little bit to the negative, it'll simply drive more silver ions from silver chloride to silver. And that'll prevent me from taking on that potential because I'm doing that reaction that will pin it back at the same value. And so if you try to, and that's why it's a great reference electrode, right? Because no matter how much charge I pass to that reference electrode, oftentimes I'm passing very little, I'm not going to be able to move its potential. It's essentially fixed, or in other words, it's non-polarizable. It's not unable to be polarized. Anyways, so there are a lot of these things. Sometimes the choice of these reference electrodes is dictated a lot by whether you are worried about any of the things in these reference electrodes potentially contaminating your solution. So for example, right, I may be weary in certain cases of using a silver-silver chloride electrode, particularly if it consists of soluble silver chloride or some other silver salt, because the silver salt may leach out of my reference electrode. So the other thing that should be pointed out is the reference electrode is usually separated from the solution by a porous glass frit. And that porous frit is to minimize the flow of solution from the reference electrode out into the main solution, because if it did, it could convolute your measurement. That's something to bear in mind in a lot of chemistry. Okay, this is actually a good place to stop. So what we'll do next time, next Tuesday, is kind of dig a little bit more deeply into the kinetics of elementary charge transfer reactions at an interface. And we'll then use that to build up the mechanisms of more complex reactions, whether they be outer sphere reactions or even inner sphere reactions at an electrode surface. So we'll kind of do a pretty exhaustive treatment of that. But this is a lot to digest, so I'll stop here and we'll pick this up next Tuesday. All right, thanks everyone.